to a better percentage. So this one is 73%. It's not good enough. Let's say we want to improve it to 89%. In other words, 0.89 lagging. That's how we want to improve it. Now, the question here is, what is the value of capacitance to be connected in parallel in order to improve the power factor from 73% to 89%? So, question, find C to be connected to improve power factor from 73 to 89%. So that is the question that we have. Find the power factor to improve the capacitance to improve the power factor from 73 to 89%. All right. So how do we do that? The first thing we want to note is that I'm now present. You get the picture, right?
No.
Okay, let me find somebody who can. Sabelo.
Yes, sir.
Do you understand what I've said now? I've given you a picture. I haven't solved anything.
Oh, I saw something, but I was a little bit confused. But I heard you saying you want to improve that power factor to 80% to 89%. I think it's what you said.
Well, yes, but what is confusing you? I thought by now we know what we mean by power factor.
Yes, I know, but not much. I know a little bit.
Okay.
Still having some questions on power factor. I was
All right,
I will ask.
What is your question?
Oh, let me go back in there. From a power factor, I know that a power factor is a ratio of the true power and the apparent power, isn't it?
Mm-hmm.
So what I was confused by is that an apparent power, it is the RMS times IRMS. Where is that IRMS coming from? And if that RMS is the current that you are given on the circuit, what about that I squared R from a true power? Is it the same current or what?
Okay. Let's go back, right?
Yeah, we can go back. Maybe
this is the source. The source is connected to a resistor. This is an AC source. It's connected to a resistor and it's drawing a current I. What is the power developed in the resistor? It is I squared R. Correct?
Yes, you are correct. That is a true power.
Yes, I wrote P here.
Yes.
All right?
Yes.
This we know. This is RMS value, this current. Right? We know this from, I don't know, maybe from matric and so forth. If you have got an AC source supplying a resistance value R, the power that is developed is IRMS times squared times the resistance. Or we can write this as V RMS squared times divided by R. correct? Or we can write this as VRMS times IRMS. These equations all give us the same thing, the real power that is used by the resistor. Correct?
Yes, you are correct.
Let's talk about a general impedance. We have got the same AC source. Now it is supplying a general impedance. The impedance is Z is equals to R plus JX. Right? And there is a current I. Right? There is a current I flowing in the circuit. RMS. Right? I told you that as soon as we start talking about power, remember it's RMS we are talking about. Right? So there is a circuit. Now notice that this impedance has got a real part and a complex part. Right?
Yes.
So if we ask, what is the power? We are not going to get P as in real power because of the presence of this complex value. We can write that the current that is going to flow in this network is going to be the V RMS. You see that, divided by the impedance. That is the current. Right?
Yes, yes.
And we can say that from this equation here, this thing just changing colors all the time. This expression here, all right, or this expression there, tells us that the power is going to be V RMS times the current, which is this current here, which means it's V RMS over Z. If you multiply this here is now power. But remember, Z in the denominator is a complex quantity, right? So when you multiply and do your division, you are going to get VRMS square over Z. The result of this expression here is not going to be a real number. It's not P, but it's S, because it's going to have a complex, you see, component, because Z is complex. That is when we said this can actually be broken down into P plus JQ. All right? P plus JQ. Are you with me? Hello? Are you with me behind the screen?
Yes, that's correct, sir.
Yes, I need to hear
Yes,
that.
sir.
So now, because of
move.
this relationship, S is equals to P plus JQ. That is where we say this component here is not real power. This is apparent power. And this is real power. Sorry, this is reactive power, Q, right? This is real power, this one. And then your S, this here is the apparent. This is reactive power, not apparent. This one is reactive. Q is reactive, P is real, and S is apparent. And we said we can draw a power triangle. You see, if you follow what I post on Teams, I sent you yesterday a very short video, about 8 minutes, that very, very clearly explains to you. And they explain it exactly the same way I've done it to you. All right. Now, if you have these three quantities, these quantities are a point on the complex plane, and they form the three sides of a right angle triangle, where the hypotenuse is S, the opposite is Q, and the adjacent is P. This angle here, from geometry, we can find it. It's tan theta is equals to Q over P, or cos theta is equals to P over S. These are trigonometric ratios that we know from maths. All right. I don't like this string. This is S. You see that? And this is what we called it the power factor. I explained it before, so I'm not going to explain again. I gave you examples of pulling a weight and things like that, trying to explain so that you can see what we mean, when I was saying, how do you calculate work? The horizontal component and the distance, vertical component is similar to reactive power and things like that, right? And in addition to that, if you look at the notes that I've posted to you, there is also a 3-page or 4-page document, PDF, which gives you another view of filling a cup with a fizzy drink and explains to you what is the reactive power, what is the real power, and what is apparent power. So this is where we are. Now, we explained the need to have power factor as close to 0 as possible, right? Because if the power factor is as close to 0 as possible, then it meant that most of the power that we are generating is actually used to drive or to give useful power, the real power. So your desire is to actually get cos theta as close to 1 as possible. All right? In practice, it's not possible to get cos theta equals to 1, but you can get it as close to 1 as much as possible. All right? Are you with me?
Yes, can you also try to upload all the videos on Blackboard, sir?
You see, I tried to do that last time and I couldn't understand what is happening. We are recording and those videos, I don't see them, and some of them are very short.
Yeah.
You see, like now I'm recording, right?
Yes, you are recording.
So, yeah.
But any video.
But go to Blackboard. There are some videos there. Check in Blackboard. I keep repeating the same thing every day, right?
Oh, yeah.
Let's continue. Now we have a scenario. You see, the whole idea is that we must improve power factor in order to get more real power out of the supply. We mustn't, if you look at a situation where the power factor angle is 90, it means for that scenario where your power factor is 90, your power factor angle is 90, It means when you say S equals to P plus JQ, right? If the theta is equals to 90 degrees, it means P is actually equals to 0. So you are sending a certain amount of current down the line to the load, but actually you are not receiving any useful power out of it. All the power is reactive. You see? Now there will be current flowing in the line. And the line itself, if it has got resistance, no matter how small, a certain amount of power is just going to be lost. All right? So that's not a good thing. On the other hand, if you have your power factor or power factor angle equals to 0, it means Q is 0. So whatever power you are sending from the source to the load, all of it, in theory, is being converted to real power. And that is what you desire, right? So the situation, as I've painted it before, you now have a motor. Okay, somewhere else. You now have a motor where the initial power factor 1, is 73%. The voltage is 400. And the current is 31 amps. But you need to improve this power factor to 89%. That is what we want to do. And the question was to find C to be connected in parallel with the load such that you would end up with a system like this. This is your motor. And here you are going to connect your power factor correction capacitor. All right. And this is 400 volts. So this is the load, which is a motor. Maybe it's driving a certain, load, a gearbox, whatever the load is. But the picture is that we would like to improve the power factor from 0.73 to 0.89. The question is, find the value of capacitors required to achieve that. Now remember, we are operating at 50 Hertz. That's the frequency, national frequency in most countries, including us here in South Africa. There are some countries which run a different frequency. For example, I think America is on 60 Hertz. Japan uses 2 frequencies. One side is on 50, the other side is on 60, and so on. I think most of Europe is sitting on 50. And so, all right. So now, how do we find this? Do you get the picture now?
Yes, what you draw is it, but I don't know what picture you're talking about. The one that you draw here. This one.
Yeah, the same.
Oh, we see this one, what you draw, so we see.
Yes, I'm repeating, I drew it at the beginning. Remember, I had to explain again. I'm repeating, I haven't changed the problem, right?
Oh, yeah. We see it.
So now, the solution now. So the question is to find the value of C that will allow you to improve the power factor from 73% to 89%. So initially, you have 400 volts and 31 amps Remember, this is an inductive load, so these power factors, they are lagging. This is a motor, right? So here we go, the solution. The apparent power is going to be the voltage times the current conjugate. All right? Now, the voltage is 400.
Before we move, sir.
Yes, let me write this. The current is 31 angle theta in brackets conjugate. Yes.
Oh, the current, the power is voltage times the current conjugate.
Mm-hmm.
That's the formula, or that conjugate you are putting it to make it.
Okay. I have explained it before when we started power factor, right? If you were here last week, I actually went through the derivation of S when the load is purely capacitive.
Oh, yeah.
You remember that?
Yes, now I remember.
Okay. There's things which I avoided to do because there's a lot of maths, and I didn't want to get bogged down by that. I'm just giving the concept. All right, but when the picture is fully clear, maybe we'll come back and explain that stuff. Now, you will see that if the load is inductive, which it is in this particular example, then the angle theta, remember it's simply cos minus 1, 0.73. That is the angle you are starting with, right? And somebody can calculate and give me the angle. I left my calculator, I don't have it here, right? Can you calculate the angle, arc cosine 0.73?
It is
43.11.
Okay, just one decimal place, 14.1 degrees.
43.11.
Okay, thank you very much. 43. So 43.1 degrees. And then the magnitude of the current, remember the magnitude, and remember it's all RMS. I'm not writing RMS here, right? It's 41. Well, we know it's given, it's 31, right? There's no need to calculate it. I want to rub. So I now, the current in phasor form is 31 angle. Remember, this is an inductive load, so the current is negative. So it's minus 43.1 degrees amps. That is the current. You see, it's lagging. This sign here is negative for the angle. And therefore, it is equals to 400 times, right? 31 angle minus 43.1 degrees conjugate, which gives me, if somebody can multiply and give us the numbers for P and Q. or just give us in polar form. The angle in polar form will be 43 because that angle changes to positive. And then it will be 400 times 31, which is 400 times 31.
It is 12,400.
12,400. So this is the apparent power, you see, and it's in volt ampere, the units. That is the apparent power.
What is the sign of the angle, sir?
It has changed to positive after this conjugation. It was negative for the current because it's lagging, it's an inductor. Are you with me?
Yes, sir.
Mm-hmm.
So, if I may ask,
Mm-hmm.
that conjugate sign, it didn't change locuzan when it is in a rectangular form.
Mm-hmm.
So, if it's changed in a rectangular form, oh yeah, it will be positive. Oh yeah, okay.
Okay, all right. So now this here is the apparent power. So now we are going to draw the power triangle. So this is my very bad straight line. Should be better than that. Let me try again. Okay. This is my right angle. Now
So
remember,
if I put that in the calculator, I get a negative angle.
which one?
The one 400 times 31 angular minus 43,1.
It's because you did not conjugate.
Oh, conjugate.
Mm-hmm.
Oh, Wamshan.
This angle here is the power factor angle, which is 43.1 degrees. And this is the apparent power, the hypotenuse point. We'll use kilo, all right? So it's 12.4 kilo volt ampere, all right? And if you have got the hypotenuse and the angle, it means you can find the value of P, all right? P is simply 12.4 cosine of 43.1. And you can also find the value of Q. I'm going to call this one Q1. Q1 is going to be 12.4 times sine of 43.1. So can you calculate for me there? Somebody calculate P and somebody calculate Q. P and Q. P and Q.
P is 93,000. 9,300 and
Let's just call it 9 point what?
9.3.
Okay, this is kilowatts.
Yes.
All right. Then Q1, it's 12.4 times sine of 43.1.
8.2 kilo.
Kilovolt ampere reactive, all right? So that's kilovars. So you see, this is the situation before power factor correction. Now, this angle corresponds to the poor power factor of 73%. Now we have to do something in order to improve the power factor to 89%. So in order to improve the power factor to 89%, we do that by adding a capacitor. So we are saying cos the new power factor angle, cos 2 theta, is equals to 0.89. That is the new power factor angle. So we are going to find this new power factor angle. And
it is 27.
Sorry?
Oh, I was saying the angle, but you can continue.
Yeah. It's fine. That's what is
27.1.
27.1. So
Yes.
we need to change this angle from 43 to 27.1, as I have indicated here. What is not changing is the real power, because we need to keep the same real power to the load. So we are going to change the angle to 27.1. So in this new angle here, the real power is staying the same at 9.3. So what is going to be the new Q2 this here? Q2. This new Q2 divided by 9.3 will give us the tangent of 27.1. Therefore, Q2 is going to be 9.3 times tan, 27.1, which is equals to, you calculate that for me.
That is 4.8.
4.8.
Yes.
4.8 K.
Okay, that's 4.8 kilovars. All right.
Before we move.
So this distance here is 4.8 kilovars, that distance.
If I may ask,
Mm-hmm.
your question now, I think it is answered that if we want to improve if you want to improve
Perfect.
the power factor, we have to decrease the angle.
Correct.
Okay.
Yes, because you see the cosine 0 is 1, but cosine 90 is 0. So when you want to improve power factor, it means you must get the angle smaller. All right? Because of the nature of the cosine ratio, it is 1 when the angle is 0, and 0 when the angle is 90. So the direction of improving the power factor is decreasing the angle. Right. So now here we are moving from 8.2 Q1 to 8.2 to 4.8, sorry, Q2. Therefore, the change in reactive power, right, is actually 4.8 minus 8.2, which is equals to 4.8 minus 8.2
Minus 3.4.
minus 3.4. This again is kilovars reactive. So the change we are looking for is minus 3.4. kilovars. Now remember that you are looking at the reactive power being reduced from 8.2 to 4.8. That reduction can only be possible if you use a capacitor. The capacitor is the one that is going to give you negative reactive power, right? When you can now add the minus 3.4, you add it to 8.2. The situation is this, right? I'll move. All right, let's expand. Draw or that one. So the situation we have is this. Initially, Q1 is equals to 8.2. I won't write the units. And we introduce a capacitor. Remember, on this phasor diagram here, or this power triangle, this is your zero line, right? This one, continuation of this. This here should be minus 3 point, did we say 3.2?
3.4.
Or minus 3.4. So this is your Q2. Q2, shall I call it Q2, okay? Right? So that the net reactive power, when you add 8 minus 3, 8.2 added to minus 3.4 will actually give you what you are looking for.
That is 4.8.
Which is this 4.8, right? So this is 4.8 now, right? That's what we are saying. So now, in order to get that 4.8, we know this 3.4 has to come from a capacitor. And the reactive power, Q now, from a capacitor is V squared, the voltage across the capacitor, divided by the impedance of the capacitor. As we have seen from the beginning, if you remember, I wrote this equation, all right? When I was explaining the issue about the real and reactive power at the beginning, when somebody says it's not on the same page. So now, for a capacitor, 1 over ZC is simply equals to omega C, right? Remember, the impedance of a capacitor is 1 over omega C, the magnitude. I'm talking about magnitude, right?
Yes, yes, yes.
So if you take the inverse of this, it just gives you that 1 over omega C. And therefore, we are saying that omega C V C squared should equals to 3.4 times 10 to the power 3. Remember, that is kilo. All right? Therefore, you can substitute now, because omega is 2 pi f. Therefore, you can say the capacitance C is equals to 3.4 times 10 to the power 3, all divided by 2 pi times 50. 2 pi times 50 is omega, times V squared. They are in parallel with the source. So this is 400 squared. And then you calculate that, and then give me the value of the capacitance in microfarad or whatever, right?
Yeah, Puma, the answer no 5.
What's the answer?
It is 0.68.
What?
A macro farads.
Okay, do we agree? Anyone else? The same answer? You said 0.
67,64.
6.
That is 6,76.
67,64 microfarad.
67,64 microfarad.
Thank you. 67.
Convert.
64 microfarad. So this is the value of capacitance that you would need to connect in parallel with the load in order to change the power factor from 73 to 89%. So if you can do that, you would have achieved the specification, which is to move from 0.73 power factor to 0.89 power factor lagging.
How many marks is this?
This is a tutorial. We are not talking about marks here. Okay, are we together? Are we on the same page?
Yeah.
Yes.
Okay, so let's close off this section. What we are actually saying is that we can summarize it. This equation we have seen before. It's not the first time, all right? Now, if we have to correct power factor from θ1 to another angle, let's call it θ2. This power, real power, staying the same. Then we can say that omega C squared is equals to P in brackets cos θ1 minus cos θ2 in brackets. No, wait a minute. It should be θ2, right? Let me correct that. It's cos θ2 minus cos θ1. Remember, θ2 is the smaller angle, so it will have a higher value of cos theta, or the capacitance is equals to P all over 2 pi f V squared in brackets cos θ2 minus cos θ1. That is the formula. So the steps that I've gone through is just to illustrate. This part here is where I was saying Q2 minus Q1. That is what I'm saying by this part. So, but you can do it in one step, that the value of the capacitance equals to that. But of course, this, we are looking for C. My friend, they're asking how many marks. In a test or in an exam, the situation can be changed around, you see. Here you are looking for C. There is nothing that stops anybody, if they want to test you, to give you some other parameter and maybe not look for C, but maybe look for theta 2. It means you will have to solve this whole equation to find theta 2. Or maybe give you another parameter, because if it's one equation, you can make one of these variables unknown, and then you'll have to work backwards to find the unknown. So it's not always that you are going to find C. The question can be twisted in such a way that you find yourself having to find maybe P, or having to find theta 1, theta 2, or whatever the case may be. But this is the principle that you are going to stay with. Are there any questions? Now, I want to give you a supplementary question, right? And for that, I will give you 10 minutes. You work by yourself wherever you are. But please do work. Don't just wait for somebody to give you the answer. If you do that, you are actually not learning, right? And you will find out in a rude way when you are given a test or exam. So the supplementary question is as follows. Right? Comparing the situation corresponding to, or comparing the two situations. You can put here two situations, right? Comparing the two situations. I'm just going to use a shorter word, the two cases, right? Estimate the percentage change in power loss. Please, I want you to seriously do this question by yourself. So if you are going to do this and get the estimate correct, then you can close your book and you know that you have understood what we had to communicate under this chapter. If not, then of course it shows that you still have that gap to close. I'll repeat again the question and I'll give you 10 minutes. I said comparing the two cases are one when the power factor was 0.73 and the other case was when the power factor became 0.89. And I'm saying estimate the percentage change in power loss, full stop. So there you go, 10 minutes. This is 5 o'clock. I'll be back at 10 past 5. Thank you. Can you just explain how you got it?
Oh, yeah. Yeah. That is a change in Q. That's change in Q. I think it is the last 3.4K. Then you have that as I wanted to say. But it's negative 3.2, 3.4K over 9.3K. Then, yeah, I think that is it, sir.
Okay, thank you very much, Sabelo. I like you because you always try. Keep doing that. You are on the winning side. Now I have some more contributions. Tembani. Nkosinathi.
Nkosikhona sewuthole 20.1%.
How did you get it?
It's a inverse tan of 3,4 over 9,3.
Why inverse tan?
Bengifuna i-percentage ewudata kanje.
Okay, well tried, but not correct for both of you. All right. Let's go back to the drawing board and see how we can estimate. Remember, I said estimate. Now, here is the scenario. Here is our source. Our source, we said it's 400 volts. And on the other side, we have a motor that could be driving some kind of load. We are not worried about that. We just said it's driving a load. This is an induction motor. Now, what happens in between? Obviously, there is current flowing in some conductors. So this is the line. Now, this line is going to have a resistance. And this is a motor. The motor also is going to have some resistance. Right? Now, power that is lost. When I say estimate the power lost, I'm not talking about apparent power. I'm talking about real power. That's the power lost. The power is going to be lost in various ways. One, when you send power from the source to the motor, you are not sending that power in order to generate heat because of the resistance of the conductors and the resistance of the motor. But it is inevitable that heat, which is given by I squared R, where R is the total resistance, is going to happen. And this is what gives you the loss of power. Your sending of power is not to generate heat. This is not a stove, it's not a heater. You are sending power to the motor to drive a mechanical load. But because current is going to flow in a conductor and in the wires of the motor, unfortunately, unavoidably, you are going to generate heat. And that heat is represented by the current flowing squared times the resistance. All right? So that is the basic thing that you must know. From this, you are able to estimate. Of course, I'm saying estimate because that is not the only way power is going to be lost. There are other means through which power will be lost, but this is the main one, right? So the question then is I1. We know it was given, it's 31 amps. So the heat loss, P1 loss, is going to be 31 squared times the resistance, the total. You don't know what the resistance is, so you just say it's R, right? But now, when you correct the power factor from 73% to 89%, something changes. And I illustrated to you before, right? The situation is like this. After power factor correction, this power here stays the same. Do you remember how much it was?
9.3 K.
Okay, 9.3. And this angle, do you remember what it was? 20 what? The new one.
27.1.
Thank you. 27.1. What's your name?
Telkom Kosnat.
Oh, Kosnat. No, I like to know people who contribute, right? Kosnat. 27.1, right. You see, this is S, right? And this is Q. Now, remember how we calculate S, or how we calculate P. P, which is 9.3 in kilo, you can put 10 to the 3 here, is actually equals to S times cos 27.1, which you know, 27.1, isn't it? But S is voltage times the current. Yes, very good. So it's 400 times I2 times, because the current is going to change, times cos, this one we know it's 0.89. That's where we got that 27.2 degrees. Therefore, you can now calculate I2. What is the value of the new current there? It's going to be 9.3 to the 10.3 divided by 400 divided by 0.89. What is the value of the current?
Twenty-six
26.12 ampere. So you see what has happened is, by improving the power factor from 73% to 89%, you have dropped the current flowing in the conductors from 31 amps to 26.12. And therefore, the power loss in the second situation is going to be 26.12 squared. You have not changed the conductors and the resistance of the motor, so it is reasonable to say it stays the same. You see that? So now you can see that the power loss in case 1 is 31.1 squared R. The power loss in case 2 is 26.12 squared R. You can therefore take a ratio and say power loss 2 divided by power loss 1 is equals to, you divide those two, 26.12 squared R divided by 31 squared R. R is common, you cancel. So this ratio now is equals to 26.12 divided by 31.0 squared. What is the answer?
0.7. 0.71.
Okay, 0.71.
Yes.
Do you see your answer? So if you look at power loss 1 and power loss 2 is 0.71 of power loss 1. In other words, there's been about 29% drop in power loss just by improving the power factor from 0.73 to 0.89. All right?
Yes.
Do you see that? That is a big reduction. It can make a very big difference between having load shedding and not having load shedding. Because that 29% translates to almost like a 20, almost say 30% reduction in consumption of primary fuel that you are using to generate electricity. If you were using 100 tons of coal, that means roughly you would have reduced it to 70 tons, right? Whatever it is. So it is a substantial change in the amount of resources that you are utilizing. And hence, I'm sure you'll be able to see why then it's important to operate with high power factor as opposed to low power factor. On the other hand, if you had made the power factor even less, then you are going to see this picture. The scenario would be even 30% worse in terms of the consumption. So a reduction of current from 31 amps to just 26 amp corresponds to almost a 30% reduction in power loss. And that is because of the square law that you see here. The loss square is proportional to the current divided in the two cases squared. So a small change in the current, a small improvement in the power factor means a lot in terms of the losses, which translates to a lot of other things of benefit to a power utility.
Professor.
At that point, I would like to stop.
Professor.
Yes.
The 29 say I missed the part where you got to 29. Will you please explain?
You see the last equation. Can you see my cursor where it's floating?
Yes, I can.
Yeah, here on the left-hand side here. This ratio is power loss 2 divided by power loss 1. Do you see that?
Yes.
Right. So that's what we are saying. Let me see here. We are saying power loss in case 2 divided by power loss in case 1 is equals to 0.71. That's what we calculated. You see? In other words, if you say this power loss 2 is equals to 0.71 times power loss 1. This equation here means the power lost in the second case is 71% of the power loss in the first case. So what is the difference? It's 29% change.
Oh, get it. Okay, thank you, sir.
Okay.
I mean, I don't get it. Can you please repeat again?
No. You see, this is 71. This is 0 point. It's just a simple equation. If I write an equation like this, if I say A divided by B is equals to 2, then I say A is equals to 2B. What am I saying? I'm only saying A is twice as much as B. Whatever the value of B, A is 2 times that value. That's what this ratio is saying, right? So here, the same ratio is simply saying the power loss in case 2 is 0.71 times the power loss in 1, you see? Which means 2 is 71 over 100. In other words, the power loss in 2 compared to 1 is 29% less. You see, 29 plus 0.71 gives you 100%. These are just ratios, right? Think about it. It's not difficult to see. Yeah, this is just ratios, right? All right. You'll get it. You'll get it. Just apply your mind. Relax, right? Is there any more questions? Okay, if there are no questions. So basically, I have covered what I had to do on power factor. Of course, I did not exhaust everything. There are other aspects of power factor which I did not talk about, like economic benefit. If you have to invest on power factor, you know, how much does it cost you? Over a certain period, how much are you going to save in terms of the volt ampere reactive that you are going to inject? Because the volt ampere is going to detect the amount of capacitance. And of course, these capacitors, when you buy them, they come in banks. They are not small things, they are big, they cost money. So it's an investment. So there's things which are like, how long will it take to return your investment or to make a profit? Economic aspects of power factor. I did not cover that. That you'll cover somewhere else. All right? When you come to distribution and so forth with Dr. Numbi in distribution, or some aspects of it maybe in H3, but distribution certainly. So on that note, I would like to switch over to what I would like to introduce here. I'm going to speak to slides. I don't normally like teaching using slides, but I'm going to use slides this time and try and pick some speed. All right. So let me share with you the slide. These slides are on Blackboard. They're available to you. Slides and share. Slides. Where is my slide?
Sorry, sir.
Oh.
Sir, I want to know, after we wrote set 1, how many topics have you covered?
We are only left with this one, which I'm introducing now. And then besides...
I'm asking which topics have you already covered?
I'm answering
After
you.
the test one.
I'm answering
So, like, give me the names, like power in AC, what? I'm asking that.
My friend, we have done introduction to AC. We have done AC components, and we have done power analysis in AC circuits. And just now we finished power factor. Right?
Okay, thanks, sir.
That information is available to you, my friend. It's available on Blackboard, on this and that. I don't know why you want to know it from me. You see, you must be following these things. Don't get in the habit of being pulled by the end all the time. Right. Am I moving? Looks like I'm stuck on one place. Oh, it looks like it's moving. No. Oh yeah, okay, it's moving. All right. So I was saying this topic here is the second last main topic that we'll have to cover. This is the second last main topic. If time allows, the very last topic we are going to do talks to what we call resonance phenomena. But if we get squeezed for time, as happened in some some semesters, we did not have time to talk to that, but we only touched it just a little bit. But the main topic that is left for now, it is what I'm projecting now on the screen, network analysis, and most important one is the three-phase analysis. Now, in the past, every time I came to teach three-phase, I would see that a lot of students would have disappeared. And when it comes to the test, they fail to answer the questions, and therefore they score very poor marks. Now, three-phase analysis is very, very important to do, because from age 3, if you are going to be a power student, you are going to be talking with three-phase. So you're going to disadvantage yourself in age 3, distribution and protection. You see? So you better stay on to the very end. Now, here we arrive at this new topic in the remaining few minutes. Most of the time, we have spent it looking at, I would say, basically Ohm's law as it applies to circuits that have got impedances. Unlike in Eng 1, where you focused solely on circuits that have got DC sources and resistances. Here, we have arrived at a stage where we are able to deal with circuits that have got AC sources and that have got a general impedance, which has got a real and an imaginary component. Now, the most important tool that we were able to learn and apply in terms of analyzing AC circuits all this time has been the issue of representing AC voltage, AC current as phasors. Now, this lends itself to ease complex maths, and we borrowed from our kitty of complex analysis in terms of division, multiplication, this and that, in order to be able to solve
So
muted me. So I'm talking all this time to myself. Please don't mute me, somebody there. I've said a lot of things, you see. If you see somebody's muting me because I'm not watching the mic, just please alert me. Yeah, you can unmute, just alert me. Otherwise, I'm wasting my time. Right? Whoever has done that, because I'm not muting myself, please don't. You are disturbing me. Simple, one loop. We are using Ohm's law to divide, to find power, and so forth. But of course, circuits are not always that simple. They are complex. So we are going to meet in this unit techniques which you've already covered in Eng 1, but you were, of course, dealing with DC sources and resistance only, right? Now, this is a revision of the work which we, by now, everybody should know. If you're still having difficulty, go to Blackboard. There's a handout, a few pages that will explain to you. I think I put that same document on Teams to refresh your mind on complex analysis. Now, there is a basic network, right? You have seen such networks definitely in Eng 1. The impedances, the black boxes, now they are general complex impedances. If you now this diagram here, you can see that there are two green circles. That is our way of representing a source. In sense, you can have a current source, which is where I'm hovering there. You'll see that it has got an arrow inside. That shows it's a current source. Now, we represent the current source either by a small symbol, small letter. If you see that form of representation, we normally use to represent the time domain form of the source, by which I mean it's either a sinusoid or a cosinusoid. So I1 could be I peak cosine something, or I1 is equals to V peak, V1 is equals to V peak sine something omega t plus the first angle. If I use a capital, then I'm representing a sinusoid, but in phasor form. Now, the black boxes, like I have said, these are elements of the circuit through which current. Black dots, which are numbered in this diagram, 1, 2, 3, 4, 5. They are called nodes. Nodes are points where two or more elements are connected together. As you would remember in the PRAC, if you are going to connect a multimeter, a voltmeter, at some point you may actually end up with 3 terminals which are going into each other like that. That's a node. You see, it's a meeting point of elements in a circuit. A source is an element, that impedance Z1 is an element, and Z2 is also an element connected at one point, and that common point is what we call a node. Now, for circuit analysis, we always number these nodes. So as you can see in this simple circuit here, they are numbered 1, 2, 3, 4, up to 5. Right? Before I say another thing about nodes, I also want to speak about the blue arrows. I've got one blue arrow here, which is indicating a path between 1 and 4. Now, that path, which contains Z2, or the path from node 1 to node 3, which contains the element Z1, or any other similar, is called a branch. So a branch is simply a path through which current is going to flow. In that branch, there might be 1 or 2 elements. Just like when you are connecting 3 resistors to get 60 ohms, that in fact is one branch. But in that branch, you did not only have 3 resistors, because they were all in series. That is Z. You had 3 resistors, 20, 20, 20. You had an inductor, you had a capacitor, all in one branch because it's a series circuit. So a branch is a path which is between 2 nodes through which current can flow. So there are several branches here, as you can see. Now, another concept which we want to talk about is what we call a loop. Now, think about the entire circuit that you see as a 4-pin window. For now, forget about all these other elements. Just think of the box as a 4-pin window. 1, 2, 3, 4. 4 pins. All right? Now, in each of those pins, I can draw a closed path as indicated by the purple arrow in this first window. I can also draw the path in the second window where my arrow is. Similarly here, third window, and similarly there, fourth window. That closed path is not the only closed path which you can form in this 4-pin window. I can also form a closed path by drawing a loop which covers 2 windows, not one. So I can go here, if you follow my arrow, right? So I'm drawing a loop which is covering window 1, 2, and window 3. So that loop here. I can also draw another closed path which covers pen 3 and pen 4. This. And similarly that. Right? And of course, lastly, I can draw a path that covers all the 4 windows like that. Right? So let me unshare this one so that I can emphasize this by way of explaining. I'm looking for my OneNote. Muted me again. I'm not too sure what will be happening, but I don't think that happens by itself. Someone is just being, I don't know what word to use, but you know. All right, so let's share that. Okay, here is our drawing window again. All right, let's draw the window pane. It has got 4 Hence, it's like this, right? So now, if I form a closed path, this path here is only in one window. I can form another closed path which covers two windows. This. And I can form another path which covers all the windows. So there are three different closed paths. Of course, the ones that can cover one window, I didn't draw all of them. You can draw one here, you can draw one there, you can draw one there. So there are four of them. To cover two windows, there are also four. You can draw this one, that one, and then you can go this way, that way. There are four. But to cover all the windows, there's only one, the red one. You see? But what I want to mention is that this type of a loop, which does not contain any other closed path in its window, is called a mesh. So here I can draw another mesh. You see, inside here, there is no other closed path. But if you look at the blue one, which is covering two windows, inside this, if I had drawn this here, inside the blue, there will be two closed paths. So this form of a closed path, in terms of circuit analysis, is called a loop. Right? So here we actually have four meshes, 1, 2, 3, 4. And of course, several loops, because I've just shown you the blue one. I could draw this one, I could draw that one, I could draw this one, and then of course the big red one. So the key thing is a mesh does not have any other closed path inside it, but a loop can have one or more closed path contained inside it. All right, I hope you get that. So let's go back to the slide.
Before we continue, sir, this is the beginning of the new chapter.
100%. Okay.
Oh.
So this is the terminology that we have to be familiar with. Loop, mesh, branch, node. Now, there is another special thing about nodes. You'll see where I'm hovering, in other words, node number 5. There is a small symbol there, a dropper line with these 3 short lines. Now, in every circuit, there is what we call a reference node. The reference node is where you put the black cable of your multimeter, and then you put the red cable of the multimeter at the point where you want to measure the voltage. The reference node to be volts. So voltage is measured in every instance with respect to a reference node. The voltage at the reference node is taken as 0 volts. So it is conventional, it is common practice that if you have got 10 nodes in your circuit, for example, you can choose any one of the 10 and make it a reference node. In other words, you put it at 0 volts. And then you measure the voltage of every other point with respect to that node. I hope that is clear, right? The concept of voltage is not measured at a point, but is measured between 2 points, just like height. You don't look at 1 point and say, oh, it's 2 meters. No. You compare where the meter is reading 0 to where it's ending, and then you say, oh, the height is 2.3. You know, if you did not start on 0 because maybe your tape measure is broken and you started at 10, and when you read on the other side it's 100, you actually subtract 10 and say it is 90, because the other side is a reference, right? So, few minutes. Now, these are laws which we are quite familiar with. And you'll see that most of, not all the circuit analysis techniques, they are actually based on these most familiar laws of Kirchhoff, which is the Kirchhoff's current law and Kirchhoff's voltage law. There is no difference in what we have learned in Eng 1 in terms of these two laws. Kirchhoff's current law, or popularly shortened to KCL, simply states that the total current flow in a node or at a node is 0. And that is what this statement is saying in mathematical form.
Yes.
The total current flow at a node is 0. And then you also have Kirchhoff's voltage law, KVL, which tells us that the total voltage around a loop or a closed path is equals to 0. Those are very important, right? Next. Now, when we are determining or we are going to analyze AC circuits, there are a number of techniques that are available. The basic ones, there are 2 which we are going to look at. The other ones are refinements or, modifications of these basic ones, just to make the analysis easier. So there are a few steps that we follow if we are going to use 2 of these predominant circuit technique, analysis technique, which is nodal and loop, or sometimes it's also referred to as mesh analysis, though. So there are 2 predominant techniques. Now, of course, you would have done other techniques for reducing circuits for purposes of finding variables. I'm talking about Norton, Thevenin, and so on, all right? So, did I skip? Right. Let's skip that, not important. You can do that, right? 5 minutes. Now, this is a simple circuit, right? Which we can use to illustrate the nodal analysis technique. The steps are illustrated in the slides, which I've skipped just to come to this one. But when you are given any circuit and you want to use the nodal analysis technique, the first thing that you need to do is to identify your elements. As you can see here, they are given these black boxes. Those are impedances. And of course, the circles, as we have said, they are sources. And the impedances are, of course, given their values as shown. Then you have to identify the nodes. That is the points where 2 elements connect. And you number those nodes. If you are going to use what we refer to as the nodal voltage technique, each node will have a voltage. And we normally give a symbol to that voltage corresponding to the number of the node. So here where I am, I would have called that one node 1, and therefore the voltage would be capital V subscript 1, and so on. You see, this is node 2. I hope you see my arrow. So that will be capital V subscript 2, and so on. When we come to node 5, I have chosen that to be a reference node. And hence I've put these 3 lines here in that dropper. That symbol is just telling you that the voltage at that point is 0. In other words, that's the reference node. And then, of course, the sources are also indicated. Now, please note, these are not DC sources. These are AC sources. You can see there's a magnitude and an angle, a magnitude and an angle, and so on and so on. All right? Now, when you are dealing with AC sources, the signs that you see inside the circles, plus, minus, whatever the case may be, are there to emphasize the phase relationships between those sources, right? They are there to emphasize the phase relationship between the sources, all right? So if 2 signals, okay, let me unshare this, and then I think I'll stop at that point. We will continue from this slide here. I won't come back to this slide for today, but let me just explain something before we disappear. Unshare. To OneNote. Okay. Draw. This is a circle, which is an AC source, and it's like that. And then I put a sign here, positive, I put a sign negative. Then this is another circle, which is an AC source. I put a sign here, negative, I put a sign here, positive. You see, I can draw an arrow and say this is like this. The arrow always points in the sign of the positive, and here this is like that. Remember, these are all AC sources, right? But if you check, the signs are opposite for these 2 sources. So if you project this on the time domain now, if V1 is like this, like that, you see, then V2 will be like this. All right, it's in antiphase. So that shows you these 2 here are in antiphase. When this one is positive, this one is negative. That's why I'm saying it's emphasizing the phase relationship at a given instant in time. All right? So it shows you that at a given time, this will be positive, that one will be negative. They are in antiphase like that. If you take any time instant t, that will be the relationship. They are opposite. Now here you see this was negative, positive. Now come here, it is changed. This one is doing positive, that one, and on like that. So the signs are not the phase relationship between those 2 voltages, not to be 6 o'clock. On that point, I would like to stop. Are there any questions?
No questions from me, but I want to ask When is our test to? I heard that it is on the 27th. Then
Yeah, it changed. You just keep looking on Teams. I put the announcements there in Blackboard. I changed that from 24 to 27. Yes.
what about those who that list that was circulating that is written right?
Yeah, those ones I've got them. I'm going to talk to them tomorrow, and then we'll have to agree on a date.
Or it will be still online.
I don't want to do online. I want them to write a physical test.
Hey,
But it depends.
So what if I didn't see the list, but my name's supposed to be there on the list?
Sorry, come again.
So what if I didn't see the list circulating, but my name is supposed to be on the list?
You need to give your name to your class rep to give to me. Directly. I received too many emails. Get lost.
You are talking to a class rep.
Class rep will collect and give me a list.